So welcome to part 2 of the Computational Chemistry for Experimentalists, Module 5, study on computing reaction barriers and transition states. Now we're going to do a couple of new things this time, so I'm going to start by logging on to my remote desktop connection. The first thing I'm going to do, this is going to make life easier for us. So open up the terminal window, Windows PowerShell, and set Gauss environment equals C CCE. I have to double check the syntax here because I don't remember if it's exe or exec, but in the Module 1 handout, you're going to have all this information. Gauss exedir. So I go back. Gauss exedir is CG16W. Once we do that, it turns out, for reasons that I don't profess to understand, capital E, once we do that, for reasons I don't claim to understand, we can get Gauss View to open log files. So we're going to open Gauss View. We're going to click through all the error messages that it gives us, all the warnings that it gives us. Close that. We're going to turn off the constant beeping every time I click a thing. And now we're going to open the file that we computed in part 1. In the Documents section, we've got some output files, and there is a TS-op2. And look at that. That is our optimized transition state geometry for the transfer of a proton from the oxygen to the sulfur in thioacetic acid. We're going to do two things in this section. First, we're going to confirm that this really is a transition state and look that it's reasonable by looking at the vibrational frequencies. Second, we're going to generate an energy level diagram showing the reactant, transition state, and product of this molecule. So our first step, to confirm that this is a transition state, we have to look at a vibrational frequency analysis. If you remember, we started out this project by optimizing the geometries of the OH protonated and the SH protonated tautomers of thioacetic acid. Just a reminder, Gauss View by default draws one little stick between the carbon and the sulfur in this molecule. That doesn't mean it's a single bond. Those little sticks are not bonds. Don't trust them. Second, this is the reactant, this is the product, this is the transition state by our predictions. Third, this reactant is a local minimum on the potential energy surface, which means if I make a small change in any of the geometric parameters, a small change in the OH bond length, a small change in the OC bond length, a small change in the carbon-carbon bond, a small change in this bond angle, any of those small changes should raise my energy, increase my energy. I'm at a local minimum. This tautomer, the product, is a different local minimum. Maybe it's higher in energy than my first local minimum, maybe it's lower in energy, but if I make a small change, not a macroscopic change, not moving this proton, but if I make a small change in the SH bond length, they should go up in energy. The transition state, by definition, if I make a small change in any of the geometry parameters except one, I'll go up in energy. That one special parameter where I move downhill in energy, that's the saddle point that defines this as a transition state. So the first thing I need to do is confirm that this really is a transition state, that there's one special direction that I move downhill in energy in, and confirm that when I move downhill in the energy along that coordinate, I move either towards the reactant or towards the product. So we're going to do that by starting with this optimized transition state geometry and computing a vibrational frequency. So we're going to set up a calculation. We're going to do a vibrational frequency. We're going to use the same method as before. Later on, we're going to talk about how it's absolutely critical to use the exact same method to calculate frequencies as you use to calculate an optimized geometry. If you don't do that, your frequencies are worthless. We're going to throw out this extra keyword that we had typed into our transition state optimization input file. We don't need that. We're going to retain this, and we're going to save this file as tsup2freq.gjf. I happen to have written that before. I'm just going to overwrite it. Now we're going to go to the command line, this Windows PowerShell. Check and see that I have tsup2-freq.gjf. Run the calculation, tsup2frequency.gjf, tsup2freq.log. The calculation is running. The terminal has not frozen. It's running. The code is running. And when it's done, we're going to get exactly that. Now, there's a special incompatibility between this old version of GaussView and the new version of Gaussian that we have installed. And that special incompatibility shows up in particular for transition states. So before we go on, we've got to open tsup2-freq.log. We've got to open it in Notepad and cut out a little bit at the end so that GaussView doesn't misinterpret it. We're going to go to our File Explorer, go to the Documents folder. Remember, I'm keeping everything in the Documents folder for now, and I'm going to move it to a shared folder later. Open this tsup2-freq.log. And I'm going to scroll down through all this self-consistent field and the population and that vibrational frequencies and thermochemistry. We'll talk later about those. Remember, this is the same sort of thermochemistry analysis that we did in Module 2. And now here at the end. Right at the end, I have something that asks me if I'm converged, predict change in energy, grad, and then some stuff about the electric dipole moment. I'm going to take this stuff about the electric dipole moment and the dipole polarizability and the dipole hyperpolarizability and the dipole orientation, blah, 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 and go right up to this next set of dotted lines, get rid of it. Save that, Control S, close this, and now I should be able to open this vibrational frequency file in GaussView. The reason I want to do this, you're going to like this so much. This is going to be so cool. I'm going to close that input file and look at the output file. Now I'm going to go to Results, Vibrations. It's not grayed out because now I have vibrational frequencies in this log file. And I can look at them. I can look at the vibrational frequency. I look at the motions. Now in another lab, in a later lab, we're going to go through what all this means. This allows us to take things like IR and Raman active vibrational modes and look at them. So this one's a methyl torsion. This one's another methyl torsion. This one's some bending. It has some CH bond stretch. But look at this. Frequency minus 2103.60. That minus sign is really a sign that it's an imaginary frequency, which means that the curvature of the potential energy surface is downhill rather than uphill. This is the special vibrational mode that moves us from transition state either to reactants or to products. And if I animate this and I look at what's happening, look at what's happening. It's exactly what you'd expect. As I move along this one special degree of freedom, I move from the transition state, which is at the middle, either towards the reactant with an OH bond or towards the product with an SH bond. This is what I hope to see. This is what I expect to see. Whenever you do a computation on a transition state, you should always make sure that you do this step. Look at the vibrational degree of freedom that has an imaginary frequency corresponding to motion along the reaction coordinate, and check qualitatively, does it look like the system's moving towards reactants and products? We're going to do this later on in the next module when we do an intermolecular reaction and we look at IRC calculations. But this is good enough for now, so I'm happy with that. I'm going to stop my animation and I'm going to close this. The next thing that I want to do is I want to compute a potential energy surface, a reaction barrier, and eventually a reaction rate. Here's how I'm going to do that. So for our purposes right now, I'm going to use a Gibbs free energy barrier. So what does that mean? I need to compute the enthalpy and the entropy and the Gibbs free energy of the reactant, the transition state, and the product. I have the results done for the transition state, so I'm going to do this for the reactant. Do a frequency calculation for OH-tautomer.log. Say this is OH-tautomer freak. Run that. While that's running, I'm going to do the same thing for the product, the SH tautomer. Calcium calculation set up. I'm going to do a vibrational frequency optimization. I don't have anything special there. I'm going to retain that. Save that file. I have to make sure that I had that one highlighted. See, it saved this geometry. Run the calculation here in the terminal window. And now I'm going to prepare my energy level diagram using Excel. There are many ways to prepare energy level diagrams, and a lot of them are very, very unsatisfactory. There's lots of special purpose software out there, and I don't know how to use it, so I just use Excel. And I'll show you some tricks that I've developed for how to do this in Excel. This should also be an illustration of some of the things that I expect for when you're preparing supporting information and you're doing these various calculations. So we're going to make a new blank workbook, and we're going to have the OH tautomer, we're going to have in here, zoom in a little bit, we're going to have the molecule, Gibbs free energy in Hartree, Gibbs free energy change, and then molecule again, rather Gibbs free energy Hartree in kilojoules per mole. And so we're going to have the OH protonated tautomer, the transition state, and the SH protonated tautomer. So first thing we need is the Gibbs free energy of the OH protonated tautomer. So we're going to go to the vibrational frequency calculation on the OH protonated tautomer. We're going to do just like we did in Module 2, scroll down to the thermochemistry analysis. And sum of electronic and thermal free energies is what we're going to use now. Minus 547.569139 Hartree relative to all electrons and all nuclei being infinitely far apart. Big number on a chemical scale. We're going to open the vibrational frequency analysis of the transition state that we did already. Scroll down again to the thermochemistry analysis. Sum of electronic thermal and free energies, minus 547.526. Slightly less negative than the 547.596 from before. Do the same thing for the S-protonated product. You can do this with command line tools if you really want to, just using the grep tool or whatever the Windows PowerShell replacement is for that. We'll cover that in a different lab. We're going to choose the OH protonated tautomer as our zero of energy, so we're going to have equals this cell B2 minus $B, $2, so that when I copy and paste, this next one is going to be cell B3 minus B2, cell B4 minus B2. These energies are in Hartree. I happen to know that there is 2625.5 kilojoules per mole in one Hartree equals 2625.5 times this guy. Copy, paste. Now, what have I found? First thing I found is that the tautomerization barrier is super high. It's 183 kilojoules per mole. Second, putting the hydrogen on the oxygen is more stable than putting the hydrogen on the sulfur. It's more stable by 16 kilojoules per mole. Now, these numbers are not super trustworthy because of the level approximation that we use. This barrier is probably a factor of 2 too high relative to experiment, but it's still realistic. Gas phase tautomerization is difficult. It's not easy. When we do what you're going to do in the lab is you're going to do the same thing for a keto-enol tautomerization, and well, I shouldn't tell you the answer. What you should find as your answer is that the barrier to keto-enol tautomerization is super duper high in the gas phase. The way it really goes in solvent is something like a proton transfer from solvent molecule back to solvent molecule, or bridged by a solvent molecule. Solvent plays a big role in how fast those things tautomerize. If you have just an isolated molecule in the gas phase, your barrier to moving protons around is always super high. But anyway, let's make this into a pretty picture. The way I'm going to do this is I'm going to make 2 copies of this number. I'm going to make 2 copies of this number. And I'm going to make 2 copies of this number. I'm going to plot this in Excel as two-dimensional line plot. Here's my Gibbs free energy, delta G. 0 is my reactant. My transition state, super high in Gibbs free energy, very high barrier. And my product is a little bit high. So that's a nice way to make one of these energy level diagrams. And you can delete this. You can put a label on this axis. Titles, primary vertical, delta G in kilojoules per mole. And I could copy and paste this into PowerPoint and insert pictures, for example, using like a screenshot tool. I could take a picture of the OH protonated tautomer. Paste it in here, shrink it down in size. I would actually do this in PowerPoint rather than trying to do everything in Excel. One more tip. See how ugly that looks? I can go to File, Preferences inside Gauss View, and I can change my background color from this ugly, is that a blue? I'm colorblind, so I don't know. I'm going to change it to white. Now by default, all of my pictures are going to have a white background, so it's compatible with the other colors, compatible with the other background colors. When I do presentations, I like to use a black background. When I do papers, I like to use a white background. Oops. So I can have a nice picture of my reactant. And my product. Nice title. Actually, if I really wanted to be clever and I wanted to communicate effectively to chemists, one of the tricks that I might do is I might take this optimized geometry, use my modify bond tool, and draw the little sticks to be whatever I want the little sticks to be. If I want the little sticks to look like partial bonds to this hydrogen so that I don't get questions from reviewers and don't have to answer again and again and again, the little sticks are not bonds, I can just customize my little sticks to be what I think they should be. Whatever will give me the least amount of trouble from reviewers. So I can just snip out this guy, copy and paste that in there. And now, if I could copy and paste this figure correctly, or I could do this all in PowerPoint and save it as a single figure. That's probably the best way to do it. But now I have a publication-ready figure that shows the actual computed Gibbs free energy surface along with the geometries of reactant, transition state, and product. This is what I wanted you to learn from this lab. How to generate a transition state, how to do this QST3 optimization where you start from the reactant and the product and use it to guess at the transition state, how to use those reactant and product and transition state calculations to get a potential energy surface, computed free energy surface in this case, and how to make sure that your transition state is something reasonable. So with that, we will close, and your assignment is going to be to do this same sort of thing for an enol keto tautomerization, and you're going to find that in a gas phase, enol to keto tautomerization has an exorbitantly, unrealistically high barrier. And so the reason enol to keto tautomerization happens in solution is that the proton transfer is modulated by the solvent. And that's all. Thanks.